Okay, good afternoon, guys. Before we start, do you have any questions about anything? Any questions? Okay, so we're gonna keep going with where we were last time. So let us remember the definition we had last time. So suppose you have a function f from x to y. So this is my x and this is my y. And this is a function f. Then we say that f is onto that f is onto or surjective, either word, if. Okay. Can you write your definition in front of you without looking at the notes? It's a definition that's quite important, that you guys write it in front of you. You don't have to tell me without looking at the notes. See if you can remember it.
F is onto when all variables, like, so say for X, if there's like 1, 2, 3, 4, and then Y is A, B, C, then at least one of them hits the 3 Y's, A, B, C.
Not at least one of them.
Mm.
If each one of them.
Yeah, each one of them.
It's crucial. It's each one of them is the image of an element in X. Okay, but now we have to write it mathematically correct. I mean, that's the picture. So mathematically, what does it mean? If given any element y in y, and that's really the definition I want you to internalize. Given any element in here, I can find an element in X that exists X in X such that F will map X into Y. So that's the mathematical definition. Given any Y in here, no matter what Y is, I can find an X in X such that F maps X into Y. So that's the formal definition of onto. So, and now F is not onto. If who would like to finish this sentence? So we are negating the fact that it's onto. So F is not onto if.
There exists a y that for all x, there exists a y in y that for all x in x, f of x does not map to y.
F of x is not mapped to y. Okay, so this is definition, and usually when I test the student in class, I actually ask them those questions without looking at the notes, because it's very important to know the formal definition. Okay, so last time we left at this stage, and I gave you the example, we discussed it, and today we're going to fill in the details, so we know exactly how to fill in the details. So last time we had the following function f from n, or the natural number, to z, and it was given by the following rule. It takes an ordered pair, because everything here is an ordered pair, and m to something in z, and it was n minus n. N plus n. And no, n minus n. Otherwise, it doesn't make sense. N minus n. And the question is, after we discuss this, we realize that this function is onto. And now my question is, you're going to formally show that show f is onto. Okay. And the way we're going to show it is verbatim using the definition. It means you have to start with an arbitrary element in here. You have to give me an element in m cross n that's mapped into your arbitrary element. So, so how do we start? We start with an arbitrary element in Z. You can call it anything you want. So let me say, let Z be an element in Z. And your job is, I put into parentheses, you have to give me a pair and an M such that f of nm equal to Z. So we're starting with an arbitrary element. You have to give me a pair that's mapped into Z. Let us remember a little bit the picture last time, so you guys get back into it. So our picture last time was like this. We start analyzing what this f is doing. So I start giving you, for example, I told you, okay, let us see. So for example, this was sent to -1, 1, 0 was sent to 1. So we're trying to understand this, just understanding it. And for example, 0, 2 was sent to -2, 2, 0 was sent to 2. And after I went through this picture a little bit, now I realize it's on 2. Now your job is to prove it formally. Means I'm starting with any element. I want you to give me n and m. Those have to be in terms of Z, so that f of n equal to Z. All right, so let's see how you guys are going to do that. Okay. So I want you to think a little bit, and you have to give me n and m. Both of them has to be given in terms of Z. I cannot solve. I cannot put this equal to Z and solve like I did before, because I have basically 3 unknowns. So I cannot solve for n in terms of Z because I have m. So it's a little bit more creativity. So how we're going to show that it is a onto. Any ideas? I want you to look at this picture. If I give you Z1, so we're mapping 1, 0 to it. If I give you Z -1, you're mapping 0, 1. If I give you Z -2, 0, 2. Look at this picture to see if you can generalize the idea. Anyone? Without me saying names, it's easier. So look at this picture and see if we can make it into an argument. So I want n and I want m. Both have to depend on Z alone. Okay. I want you to give it to me. If Z is 100, what do you think we can map into it? Which term will go to 100? Quickly.
N equals 100, m equals 0.
Right. If I take Z to be -100. Rachel.
0 equals n, and m is 100.
Very good. Now make this into an argument. How do you think we're going to make this into an argument? I cannot just give you numbers because you have to show for every Z. I cannot sit here and list every Z. So how are we going to make an argument? We're going to break this up into Z positive and Z negative. Okay? If Z is positive, what should I take n to be and m to be? Now the picture should be very clear. If Z is positive, I can just take n to be Z and m to be 0. Then f of nm is equal to n minus m, it means z minus 0 equal to z. So if z is positive, I can just pick an m to be z and 0. If z is negative, I pick n to be 0 and m equal minus z. So we make an argument. Then f of nm is n minus m. It means 0 minus z, which is equal to z. So that's how we make an argument correct. So we pick any z, and you have to give me n and m. They should depend on z only. That's what they should depend on. And convince me that for this choice of n and m, the image is mapped into z.
So I have a question then.
Of course.
So are we not allowed to have any other value except z, negative z, and 0?
Oh no, anything that makes sense I will accept.
So
That's
we
not the only choice. What?
We just got to choose an argument.
Exactly, you have to choose.
Okay.
Oh, I don't care what you do.
Okay, that's where I was getting lost because I wasn't sure how to make an argument with everything. Okay.
Yeah, you can pick. So who can give me another choice? So this is one choice because the picture kind of told me that. Okay, but probably another one can give me another. Who can give me another choice quickly? Watch. Suppose I take n to be 2z and m to be z. I can do that. Will this work? N minus m is 2z minus z. This is equal to z. That's another choice you could have made. Does this answer your question?
Yes, it does. Thank you.
A lot of choices, a lot of choices. As long as you give me one, what matters is the both n and m depends on z. That's what really matters. So if you cannot give me m in terms of n and n in terms of m, this doesn't make sense. For every z, your n and m should be given in terms of z. And how many choices you have? You know, you have a lot of choices, not all the time, but sometimes you do. Right. So my last question about onto is also simple, but I want you to kind of get a picture of it. And this is my question. It's very simple. Suppose g is a function from z, all the integers, to z cross z. It means the input is an integer, but my output here has to be an ordered pair. So I'm going to give you this simple ordered pair. That's g of n. Okay, I want you to look at this function for 1 minute and tell me, is it onto or not onto? Analyze it a little bit. Look at the output. Is your output covering everything in z cross z? So as n, take every possible value of integer, is the output taking every possible ordered pair just by looking at it. And then we argue correctly. What do you think? So my question to you is G onto. Means are we going to hit every ordered pair? Anyone? So I give you any ordered pair here. Anyone? Do you think I can always find an input? Let me start. Logan, do you have any idea?
I'm a little bit lost here. I'm sorry.
So in these problems, we kind of work backwards from what it seems, because we're looking at, so we look at the ordered pair and see if we
Right.
can find an input that's going to give us that ordered pair.
Yes.
But in this case, if we have an ordered pair where the second entry is even, we can't find an input.
Absolutely correct. That's what I want you to start seeing.
Okay.
Okay, that's what I want you to start seeing. When I ask you the question, is G onto sometimes, okay? Like in this case, the question is, can I actually get every ordered pair? So if we look at this problem tiny bit, we realize that the second one is always odd. So you can never hit a ordered pair where the second component is even. So definitely it's not onto. Okay, definitely it's not an onto function. So now is G onto? No, we have to prove it. Now when we say no, we have to show why it is no. So to show that it's not onto, we have to give an element in here so that no element in Z get mapped into. So here what we say, okay, is G onto? No. Let me take the following pair. So I'm gonna call it CD. Let CD be the pair 1 and 2. So this is an output. That's a pair in G cross C. So that's me take that. Given any n, if I take any integer in Z, G of n, which is n to n plus 1, is definitely different from 1, 2. Why it's different? Because to n plus 1 is odd. However, 2 is even. So no integer will be mapped into 1, 2. Regardless which integer I take, nothing will be mapped into 1, 2 because to n plus 1 is odd, so we cannot map. We cannot get every Z cross C. So we're really moving backward. You're really moving backward. We're starting from here. And I ask myself, can I always find an element in Z that's mapped into it? Sometimes it's easy. We can solve for it. And sometimes, we just look at it like this problem. I gave it on purpose because I wanted to really interact that there is no way we can hit them because I'm only taking the odd numbers. Right. Now, another fact, and we'll do one more problem along those lines later on. Another fact that characterize functions. So if we have functions are called onto, F is called onto or one-to-one if every element here in the codomain is hit by an element in the domain. That's what is onto one. Or the range is the same as the codomain. That was our definition. Okay. Now we're going to define another concept, the concept of one-to-one. So, okay. So definition. One-to-one functions. One-to-one or injective function. Okay. So let F definition. Let F be a function from X to Y. So X and Y are two sets. And let F be a function from X to Y. We say that F is one-to-one. F is injective or one-to-one. Injective or one-to-one. If I'm going to give the definition first in words and then a mathematical definition because words get us that far. One-to-one, if the following happens, is basically one-to-one is simple. The function is one-to-one if. Suppose this is my function from here to here. One-to-one means that no two different elements of X are assigned to the same element in Y. Okay, so F is one-to-one if no two are assigned. So for with one-to-one, if this is assigned that element, this will have to be assigned another one. So no two elements are assigned the same element. So in Word, F is 1-to-1 if in words. If no two different elements of X are assigned the same element in Y. Assigned the same element in Y. So picture-wise, and then the workable definition that we're going to use to prove 1-to-1. So pictures-wise, what is the picture for 1-to-1? So that's my F. And that has a bunch of input in here. So 1-to-1 means, sometimes we write 1-to-1, no two different elements are assigned the same. So if I assign this one to that, this has to be assigned to a totally different element. This will have to be assigned to a totally different, and this one will have to be assigned to a totally different. That's the idea of 1-to-1. Not 1-to-1 means this doesn't occur. 1-to-1, it means that, so 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. Not 1-to-1 means at least two elements are assigned the same thing. That's not to one function. And the rest, I don't care. Okay, so that's the picture for 1-to-1, and that's the picture for not 1-to-1. Now, the mathematical definition. It means what we call the workable definition, the definition that we will use to show that it is 1-to-1. So mathematically, this is the definition. Okay. F is 1-to-1 if I take any two element in X, given any X prime in X, if X is different than X prime, X and X prime are different from one another, then what's assigned to them has to be different from one another. Okay, so I'm trying to write in a correct mathematical words what F 1-to-1 is. So F is 1-to-1 if given any X prime in X, if I take any two elements, if those are different, their image has to be different. Or another way, or that's equivalent to say the following. Okay, I want to write the contrapositive of that. Or equivalently, given any X prime in X. Okay, what is the contrapositive of that? If, given any two elements, if those elements happen to be assigned the same thing, then who would like to finish my sentence? I'm writing the contrapositive. So from here to here is actually the contrapositive.
Then X and X prime are equal.
Then X and X prime has to be equal. That's 1-to-1. Both definitions are equivalent to each other. And when we're showing function is 1-to-1, we can use either one. The second one would be the easiest to use because it involves equality. This one involves inequality, which is harder to work with. So if function F is 1-to-1 if given any two value of X, if they are different, that was assigned to them has to be different. Or if they are the same, it means what we started with have to be the same thing. Okay, so we're going to practice a little bit this definition. So we're going to take several examples to learn how to show a 1-to-1 and a 1-to-1 function. So let F be the following function. Okay, let F Example number 1. A simple one. Let f be very simple. The first one is going to be trivial. Let f be a function from R to R given by f of x equal to x plus 1. Okay, very simple. And my question for this one, show that f is 1 to 1. And the graphically, it's what's happening here is the following. F is basically a straight line. Okay, 1 to 1, it means if the input are different, basically the output are different. And here it's very clear. There is no different x that have the same output. So you guys probably back in high school, you were taught what they call the vertical line test, which is I don't like to use. But here, if the input are different, the output are definitely different from each other. So that's really the picture. But now how we prove it mathematically? What we have to show. What does it mean to show 1 to 1? Either you show for all x and x prime, if the output are the same, then the input are the same. Or you can show if the inputs are different, the output are different. Either one of them. That's the definition. Now, because this deal was different and this deal was equality, this is usually easier to show. Easier to use. So how I'm going to prove that my function is 1 to 1? I'm going to proceed like that. So I will write what we have to show that. Given any x prime in R, if f of x equal to f of x prime, then x equal to x prime. That's what we have to show. So how do we prove 1 to 1? We start, that's how it works. We start with 2 values in my domain. We say let x be x1, such that it's an if statement. So we would pick 2 values that satisfy the hypothesis. And we're going to prove the conclusion. Let x prime be in R such that f of x equal to f of x prime. And I have to convince you that x equal to x prime. So this is a proof. That's an if-then statement. And that's really what my goal. So we start with 2 elements. They have assigned the same value, and we have to show that x is equal to x prime. But now, as I said, this is a simple problem. F of x is to x plus 1. To x prime plus 1. I take away 1 from both sides, and that will give me x equal x prime. Hence, my function is a 1 to 1 function. Okay, so if the output are different, the same, my input have to be exactly the same. So let's do other problems along those same lines. Suppose I take f from n to n. So now my domain are all the natural numbers, including 0, and n. Let f from n to n. It's given by f of n equal n squared. And the question is, show that f is 1 to 1. Now, what do we have to show? Exactly that. So in the box, I just write what we have to prove. We say we have to prove that if I take any element, you can call them x, you can call them n, I don't care what you call them. Any 2 element in n. I want to show that if their output is the same, then the input is the same. That's really what I would like to prove. So how do we start those proof? This is an if-then statement. We say let n prime be in n, such that f of n equal f of n prime. And my goal is to show n equal to to n prime at the end. Okay, so we take two elements, such that f of n equal f of n prime, and I have to show n equal n prime. All right, so what does it mean f of n equal f of n prime? F of n is n squared equal n prime squared. Okay, right? And then I want to show n equal n prime. So what do you want me to do? It's a simple problem. N squared equal n prime squared. Can I deduce n equal n prime? Can I go from here to here? Yes or no? Quickly.
Yes.
Because?
Square both sides.
Okay, so hence the square root of n squared equal the square root of n prime squared. Okay, now what's the square root of n squared?
N.
No. Anybody else? What's the square root of n squared?
Is it
Is
the
the problem-
absolute value of n?
What?
Is it the absolute value of n?
The absolute value.
Yeah, and we're working with natural numbers, so that's a problem.
That we're going to fix that. It's the absolute value of n, because it's important, equal to the absolute value of n prime. Otherwise, you'll be missing stuff. You'll be missing things if you're not careful with that. But n and n prime are positive. So it means the absolute value of n is n, so n equal to n prime. And my function is 1 to 1. And basically here I have a function, and the domain are only a bunch of integers. I'm not taking everything as a domain. And the output are basically those points sitting on the parabola. So point like that. So these are the output value. And this is a one-to-one function. Now, suppose I take the same function and I tweak it a little bit. I'm going to tweak it. And so suppose I take f with the following function. So example number 3. Suppose f is a function from z to n given by f of n equal n squared. So I kept basically it's the same rule with squaring. I'm changing my domain. Okay, and the question is this function one-to-one? And what's the importance of domain? So is f one-to-one this time? If yes, we prove it. If not, also we show why it's not. So back to you. Is this function one-to-one?
It's not, because we can get the same output with different inputs.
You can get, okay, it's f one-to-one, and the answer is no.
So we could put in, so z allows us to put in an input that's negative, but since
Right.
the output gives us a square, it could be, so -2 and 2 is going to give the same output, but they're
Exactly.
different.
F is f one-to-one. The answer is no, because. What does it mean not one-to-one? Not one-to-one, it means you can find two different elements of x that are assigned to the same element in y. So here, because let me take n to be 1, 2, sorry, and n to be -2 or n prime. Then n, of course, is different than n prime, but f of n is equal to f of n prime is equal to 4. Okay, so this function, when I changed my domain, then immediately I created the function became not one-to-one. And that's really one reason tells you when we define two functions to be equal, I did not say two functions are equal if they have this given by the same rule. I said two functions are equal if they have the same domain, codomain, and the same rule. because equality, if two things are equal, they should have the same properties. So now here, if I take this function and the previous one, even though the rules are the same, but they don't have the same property. One is 1-to-1 and one is not 1-to-1. That's why equality between function has to require everything. The same domain, same codomain, and of course the same rule, which is the important idea. So this is function is not 1-to-1. So let us now write down what does it mean f is not 1-to-1. So f 1-to-1, we defined it. So f, suppose f is from x to y. F is not 1-to-1 if, who would like to write the definition for me? Basically, I'm going to negate the fact that f is 1-to-1. Okay, so I'm going to negate this. 1-to-1, it means given any x, x prime in x, if f of x equal f of x prime, then x equal x prime. Now we're going to negate. Who would like to negate it in a formal way? For every x, x prime, we negate it if there exists x, x prime in x, such that f of x equal f of x prime, that's the negation, and x different from x prime. So f is not 1-to-1 if you can find two input values which are different from each other, but they have the same, we assign to them the same value. Let's see one more example along the same line, where I'm going to ask the questions that involve both 1-to-1 and onto. Okay, so my last example is like this. So example number 4. I'm going to give you, let f be the following function. The input and the output. Okay, and it's defined by. So the input is in ordered pair, and the output is in ordered pair. So I'm going to define this to be equal to, let us say, m plus 4n, and then. Okay. So question number 1. Show that f is 1-to-1. Okay, and question number 2 is going to be show that f is onto. So how we're going to show that f is 1-to-1? We're going to start with 2 elements in the domain. Now the domain are ordered pair. I need 2 elements. So we're going to say let m n, 1 element, and m prime and prime be in z cross z, 2 elements in the domain. And I want them to have the same output. So it means f maps them to the same thing. That's how we start the proof. And what we have to show, and I put what we have to show in red, and we have to show that mn equal to m prime n prime. Okay. So as I said, there are 2 equivalent definitions for 1-to-1. We have 2 equivalent definitions. And honestly, you can use either one. The way we prefer to use this because it gives me an equality to work with. This one gives me different, which is harder to handle. That's why we always work with the second one. Okay, so now here we are. We have 2 ordered pair that have the same output. I want to show that they have the same input. So let us follow basically our nose. So this is my hypothesis, and I need to get you to the conclusion. So let's see. F of mn So that's my hypothesis, equal f of m prime n prime. Gives me that. What is f of mn? Means m plus for n equal m prime n prime. Okay. And now you have two ordered pair. If those are equal, so it's going to give me the following. M plus 4n equal m prime plus 4n prime and n equal n prime. Remember, my goal is to show that the ordered pair mn is equal to the ordered pair m prime. So I already have n equal n prime. And now if n is equal n prime, and I have the first equation, I can conclude m equal n prime. So we have n equal n prime. But since m plus 4n is equal to m prime plus 4n prime, so this gives me that m plus 4n equal m prime plus 4n. I'm using the fact n equal n prime, hence m equal m prime. So the pair mn equal to the pair m prime n prime. Okay, so that's an exercise how to prove this one-to-oneness. Okay, so we start with the ordered pair that have the same output. We argue that the input will have to be the same. Part 2, we're going to show that this function is onto also, just again to remind us how to show the onto property. Okay, I'll move on to the second page. And I'm going to take the same function and I'm going to show you it is onto. Again, because to build the flexibility with that. So again, question number 2. Show f is onto. Is onto. All right. Again, that's my f. I rewrite it. And the rule is it takes an ordered pair mn to m plus 4n and then. Okay, how we're gonna show it is onto. To show it's onto, I have to start with a pair from here. That's where I should start. And then I have to give you an ordered pair in Z cross Z that's mapped into it. So I have to start, because I told you onto. I'm not this time telling you is it onto. So I have to start with an arbitrary element in here. You can call it anything you want. So let CD, for example, be an element in Z cross Z. My CD is here. That's my ordered pair. What do we have to show? Okay, what do we have to show? We have to find Mn. You have to give me what M is and is such that F maps Mn into CD. No matter what C is and no matter what D is. You have to give me the Mn. That's really my goal here. So I put that in red. That's what I'm really heading. All right. It is your heart. So whenever I'm working with onto, I actually like to work. I move to the side and I scratch because so I can understand here. And then I copy what I realize. What do I mean by that? What do I want? I want Mn such that f of Mn equals CD. So it means I need to find Mn. So that's my scratch. You can write it if you want, or up to you, such that M plus 4n equals CD. In this scenario, this is the known. It means I have my CD. And the unknown are the n and the m. That's really what's happening in this scenario. That's what I thought. I'm giving you this, and now you have to give me n and m in terms of C and D. All right, in this picture, okay, I can pick n to be D. And I am within my domain because D is in Z. So as simple as that. Now, what shall I pick my M to be? Back to you. Quickly. It's a fairly simple scenario. What is M equal to? I want M plus N to be equal to C. So for this equality to hold, it means I take M, so that's still my scratch, because that's when I sometimes fear what's going on, to be C minus 4N. Okay. But M cannot be given in terms of N. Your M and N has to be given of the quantity which is known, which is the C and D. But I already know that N equal to D, so my M should be C minus 4D. That's what I think should happen. Now I ask myself, am I within my domain? Okay, my N is my domain, my M is, C is an integer, 4D is an integer, it's also in my domain. So I am definitely in a good position. Now I will write what we did. So now we say let CD to be Z cross C. Let N, we're gonna choose N to be equal to D. So at this stage, because you have to give me Mn, and let's choose M to be C minus 4D. So we do the scratch so we know what our Mn. And then let us verify that F actually sent those Mn that I chose to CD. Now I'm going to verify that this is the case. So I start here and I go backward. I'm going backward for the onto. Okay. So now let us compute. What is F of Mn? Based on my choice, M is C minus 4D. Based on my choice, N is D. So this is equal to what? What does MF do? It takes the first component, add to it 4 times the second component. And it leaves the second component by itself. So this is going to give me CD. Check. Okay, so that's how we work with basically onto. First we have first we do scratch. And we ask ourselves, okay, I'm going to start with an arbitrary element in here. Can I find something in Z cross C that's mapped into it? That's the known. That's really what I know. So the question, can I find N and M in terms of C and D? So I do some math. And when I do this piece, that's when I start realizing if it is onto or not. This is really going to get me somewhere. If I was able to find the N and M within my domain, then I go back, okay, that's my N and that's my M. And then I verify that my choice is right. It means was my choice actually hit the point C and of the proof. Okay, so this is an example of a function that satisfies both property. It's one-to-one and onto.
Professor, I'm lost with the plus 4D part.
This one?
Yes.
Yeah, okay, let's go back. What's the rule here? What does F do? Takes the first component and does what to it? It adds to it 4 times the second. Got this part? That's the rule. And here it does what? It keeps the second component the way it is. Okay, so for example, suppose I take this function and I ask you to compute f of 2, 5. What is f of 2, 5? What's my rule here? What's f of 2, 5? It's 2 plus 4 times 5. What's the second entry? Understand how the function work?
Yeah.
Okay, now let me go back here. I chose my m to be c minus 4d, and n is d. What does my function do? Takes the first entry, whatever it is, add to it 4 times the second. So if I am right here, what is f going to do? Takes the first entry and add to it 4 times the second. And the second one, it keeps it the same. Now, minus 4 plus 4 give me a c, and this will be a d. Is this make more sense?
Yeah.
Okay, all right. So basically what I'm doing in my mind, actually what really we're doing is you don't have to write this because whatever. So suppose I take 20 and 5. This is my CD. And my question is, what should be the term that goes in it? So that's really the argument, but I cannot make it for numbers because I have to show it to you in general. What's go to it? So my question is that, okay, I was really after those. What should n m? Sorry. So this is 25. And my question is, what m and n should go to that? So this would be m plus 4n and n. That's really my job. So if I give you that, what m and n, which are mapped into it, I said, okay, the one mapped into it, your n has to be the 5, and m plus 4n should be the 20. It means your m has to be 20 minus 4n. It means 20 in this case minus 20 is 0. So it means this one has to be 0, 5. And 0, 5 is actually mapped to 25 because what f does, it takes the first plus 4 times the second, which is going to give me a 20, and the 5. So that's really what we are doing. So that should remind you the inverse function. You have the output. We're finding the input in terms of the output. Right. So we defined the notion of onto. We defined the notion of a one-to-one function.
I have a question about the scratch.
Of course.
So in this one, we had m plus 4n and n, which is we were able to define n equal to d. But what if both the first and second component had m and m in it? So like,
yeah,
say
I was planning to give you that as a homework.
Oh, okay, okay. All right, I'll let it be then.
Yeah, that was your homework. You have to solve for it. It's not hard.
That's what I figured. I didn't know if I
Yes.
guess starting out was what the question was about, but that's fine.
Yeah. So you just solve, and as you're solving, you ask yourself, I am in my domain, yes or not? And this is going to tell you, is it onto or it's not onto? Are you with me?
Yeah.
So I'm going to assign this as homework for next time. Actually, I'm going to do it as a practice. So not to make you write more. Yeah, exactly. And that was, as I said, that was plan. I did that to plan for the homework. Okay. Now, what's a bijection? So we defined the idea of a one-to-one and onto. Now, what's a bijection? A bijection is a function which is both one-to-one and onto. Okay, so definition. Bijective function bijective function or one-to-one correspondence. So or one-to-one correspondence. Okay, so let f be a function from x to y. X to y. Then we say that f is bijective or f is a one-to-one correspondence. Both are used one-to-one, correspondence. So they add the word correspondence to instead of writing onto, if f is 1-to-1 and onto. So a function is called a bijection if it satisfies both property. It's 1-to-1 and onto. So the simple picture that I'm drawing, actually, even though they are simple, but give us a picture what's happening. 1-to-1 means, a bijection means, so suppose I have that here. Next time we will watch if I have infinitely many. So 1-to-1, it means if this, every term has to be sent to a different term. This have to be sent here. This have to be sent to a different term, a different one, and a different one. That's a bijection. So it is 1-to-1 and onto. Every term in the output, every term in the codomain is hit by a term in the domain. And no two different terms are sent to the same thing. That's a bijection. Now, we just saw one, we just saw a minute ago, but let me, for example, give you a very simple one. Suppose I take the function f be a function from, let us say, R to R, and given by f of x equal x to the power 3. So f is a bijection. Okay, and we're gonna prove it. So because first f is 1-to-1. Why is f 1-to-1? I pick two elements in the domain such that f of x equal f of x prime. So if I take two elements that have the same output, and I wanna convince you, which is simple in this case, that the input will have to be the same. So if f of x equal to f of x prime, this means that x to the power 3 equal that. It means the cubic root of x cubed should be equal to the cubic root of that. It means x equal x prime, because the cubic root of x cubed is exactly f. So that's the 1-to-1. f onto. Onto, I start here. Then I back up here. So I start with an element in Y, in R, okay? And my scratch, because when I hit onto, I go here, always. So my Y, so I start with Y, that's the known. And then I wanna find the X. Now in this case, we just solve. So my X has to be the cubic root of Y. I just have to solve. But now how do I write? We say, let Y be in any element in R, in arbitrary element. Pick X to be, that's how we write it. I want an X. I say, let X be the cubic root of Y. Then I have to justify that my choice is correct. Then f of X is f of the cubic root of Y is the cubic root of Y to the power 3. This is equal to Y. Okay, so the actual proof, the one that you show me, is after you do the scratch and you find your X, and then you tell me, okay, let X be equal to that. That's really how we work with this. And graphically, the x cubed function, that's the x cubed function. That's really the x cubed function. So it's definitely 1-to-1. No two input have the same output. And this, of course, it's onto. Because if I take any output value, anything in R, I can always find something that's mapped to it. That's really the ontonous. So anything here, something will be mapped into it. And 1-to-1 because no two input have the same output. So that's the picture, in graphically the picture. Right. Now we're going to define something that probably you've seen for a long, long time, and we have to define it, the notion of composition of two functions, and then what properties that f and g have will be inherited by the composition. So composition of two functions. So composition of two functions. Okay, so suppose we have two functions, f and g. So let f be a function from x to y, and g a function from y to z. Okay, we have to be careful with my domains and codomain. So this is my function here, my first function. Usually I like to draw those because, you know, help us a little bit. So I have f, it goes from x to y, and y, its domain, g, its domain is y, so I can draw it from here to here, that's my g, and goes all the way to z. Okay, that's the picture. Then the composition. The composition. The composition of f and g, denoted by f, sorry, in this case, g composed with f is defined by of course, all of you know this definition. I'm not arguing that. G composed with f of x is defined to be g of f of x. Okay. So in the picture, what's g composed with f? Means that's a new function. Okay, we have two functions. Composition is a new function. How is it defined? We take an element in here, basically. We find where f does to it, and then we see what g does to f. This function from here to here that operate this way, that's g composed with f. So that's really the composition. We start with x, we compute f of x, which is an element of y, and then we let g act on the output of x under f, and then we get g of f of x. And that's really the picture for decomposition. Now, one important note when we talk about decomposition, which is the following. For the composition to be defined, so let's note, G composed with F is defined if there should be a condition. We cannot just always talk about G composed with F. Under what condition is G composed with F defined? Let's see how we define it. It's G of f of x. So for this to make sense, f of x should be in the domain of G. Otherwise, this doesn't make sense. So the composition is defined if the codomain, of f, because f of x is inside its codomain, the codomain of f coincide with the domain of G. Okay, so we cannot just compose function the way we want. To be able to we did that in calculus. We did not even think about those ideas in calculus. We just composed anything. So we're not calculus anymore. We can compose function if the composition is defined if the codomain of f coincide with the domain of G. Otherwise, the composition doesn't make sense because of the definition itself. This input here, f of x, which is in the codomain of f, has to be acceptable as an input for G. That's why we have to be very careful. All right. So a very straightforward example. So suppose I asked you the following. I tell you that we have a function f. Okay. Suppose f is a function from z cross z into z. Okay. I will tell you later how is it defined. That's not my problem now. And into Z cross Z. Okay, those are my two functions. Question number 1, is F composed with G defined? Okay, think a little bit. Can I just compose F with G? Yes or no? You are too quiet today, guys. Very, very quiet. Okay, is the composition defined?
Yeah.
Yes, because
the codomain of G is equal to the domain of F.
yeah. What's the codomain of G? If you ever forget, you ask yourself, how is this defined? This is F of G of X. So for this defined, G of X and Z cross Z, so it has to be defined. So this and this has to be the same. So because the codomain of G coincide with the domain of F. Crucial. Now, if G composed with F defined, okay, can I define G composed with F? Again, analyze. How is G composed with F defined? What do you think? Yes or no?
Also, yes.
Also, yes. Because?
The codomain of F is equal to the domain of G.
Yeah. Usually I think about it. I said f of x. What is f of x? F of an input. It's in Z. Okay. Is it this? Can I define G of something in Z? Yes. Again, because codomain of F coincide with the domain of G. The minute I tweak the domain of F, the minute I put this to be N, forget it. Things are not defined. So we have to be very careful whether we can compose two functions, yes or no. So we cannot just compose anything we want. Okay. All right. The second question, and I would like to, we're gonna introduce now and we do it next time, is the following. Suppose I know something about F and G, like F is 1-to-1 and G is 1-to-1. And the natural question is, will the composition inherit this property? And the other question is, if F is onto G is onto. Okay, will the composition inherit this property? So that's really the second question we're gonna. So what can we say about F composed with G from the properties of F and G? Okay, so let me pick the easy part, the easy proof, and the other one I'll do it next time. So I'm gonna put the following problem in front of you and see whether we can do it. So we can, this is a fact or a theorem, whatever we wanna call it. Okay, let F be a function. So it's a rule from X to Y. And G from Y to Z. Then, if F and G are onto, or one or surjective, so that's my hypothesis, if both are surjective, then the composition. Now, which composition should make sense here? So then G, X to Y and Y to Z, it means is also onto. Okay. So if F and G have the properties that they are onto, then when we compose them, also I have a new function, and this new function will have the same property. Okay. So we have F here, and I have F from here to here, X, and this is my Y, and I have my G. Okay. F has the property that is onto. It means anything here come from somewhere. That's really what it is. Anything here have to come from somewhere. Z have the same property. Everything here come from somewhere. So something like that. Okay, everything is here. Now my question that under those conditions, I want you to convince me that G composed with F will also have the same property. Okay, so how can we do that? How can we do that? I get you started and you help me out. So first, what does it mean? G composed with F first is a function actually from X all the way to Z. That's where G composed with F. I want to show that's my hypothesis. That's my conclusion. Okay, to show this is onto. What does it mean? To show is onto. Means, again, we're moving backward. I'm going to start with any element in here. And you have to find me the element in X, which is mapped into it. Okay, so this is my Z. And since I want F composed with G, so I'm going to draw all those three if you want. So this is my X, this is my Y. And to show onto, I have to take anything here, any element, and you have to convince me that you can find something in X which is mapped into that. That's really how you guys will have to do it. So I'm going to start with any element in here. So that's the given. So I start with anything in Z. And you have to give me something in X. Convince me that there exists one that's mapped into Z. So I put those two pictures in front of you, and I want you to walk me through the proof. It's more abstract because I'm not giving you formulas here, but it's not hard. I'm going to start with anything here. And you have to convince me something is going to be mapped into it. Let's use this picture first. And then we abstract it. I'm listening. I'm all ears. You can convince me that there is something here that necessarily that it will map into this with the both property that F and G are onto. Let me follow this picture, this one, and then we make it more abstract. If I pick this particular dot in here, is there something that's going to be moved, mapped into it? If I pick this dot, I know the fact that G is onto, it means this dot comes from somewhere here. Let me call this little y. But this purple dot, because F is onto, must come from a certain X in here. So it means that if I take any Z, this X, by definition of the composition, is actually going to be mapped into Z. So I repeat the simple idea. This is my Z here. Because my G is onto, it means this had to be hit by something, because G is onto by a certain Y. But F is onto, means this is Y must have been hit by something from X. So now what's the definition of decomposition? What does the composition do? Take X and then compute F of it, and then it compute G of it. Means this X here has to be mapped into the Z here. Is anybody following? Yes or no?
I think I think I understand. From what I have is we start with we want to show that for all Z and Z there exists an X such that the composition of X is equal to Z.
Very good.
Okay.
How are we going to find this X? Okay, I'm going to write this in purple. That's Z and Z. We have to show. I write verbatim what you told me. It exists in X such that G composed with F of X equal to Z.
So I said I have let Z be in Z,
Right.
and then we know that G is surjective, so there exists a Y and big Y
So
such
since
that
G is onto or surjective,
yep. So there exists a Y, a little y and big Y.
there exists a Y. I'm writing the picture.
Such that G of Y is equal to Z. And then we know F is also onto.
He's right here. You're absolutely correct. He's right here. Now he's right here. Now he's going to back up one more step. Okay, keep going.
And we know F is surjective as well. So there exists an X and X such that X is equal to Y. And then you kind of just put that all together in the composition.
F is also surjective. Hence, I can find an X in X such that F will take X to Y. So his first step, his Z is here. Then he said, you know, G is onto. So this Z here is the G of a certain Y. When he said, you know, but this F is onto, it means that that you can find an X in here, which is mapped into that. So this Y is actually the F of X. That's basically what he's telling me, verbatim. But now the definition of composition. Because now if we look at, so this is my X in here. If I take G composed with F of X, it's equal to G of F of X. It means G of Y, which is equal to Z. I will put the whole thing together. So we started with arbitrarily Z and Z, anyone. And then we were able to find an X in X such that the composition will send X to Z. Therefore, end of the proof. So if you have two functions, if they're both surjective, then when you compose them, also their composition is surjective. And that's really the picture. The picture is a little bit, make the proof actually simple for us. We start from here, then we back up. From here, we back up. This is the X I am after. That's going to be mapped to Z under the composition. Okay, for next time, for Monday, I know you have your homework, but I'm going to assign a few practice problems. You don't have to write them, like few practice problems from the book to give you some flexibility with one-to-one and onto, okay? And that's it. You guys have any questions?
Are you going to be at your office hours today?
Yes, 3:45 though.
Okay, 3:45.
Yeah, because I have an linear algebra class and sometimes it runs over because I have a quiz. So 3:45, there will be no problem.
Okay, great.
Okay, so if anybody has any questions, I'm in my office at 3:45. All right? Okay, bye-bye, guys.